Thank you for your attention for my talk. In this presentation, I want to tell you about the GPT-2. Before I start talking about the GPT-2, I want to give you a little bit of context about the work we've done at OpenAI. Oh yeah, one other note. Even though the schedule says my talk is 1 hour long, in reality it's going to be only 30 minutes long, so we'll have a bit of a longer period for questions and answers. Okay, to get started. OpenAI has done a fair bit of work in reinforcement learning. Some of the most exciting work we've done in reinforcement learning is on our Dota 2 bot, OpenAI 5. At this point, many of you should be familiar with it. Dota 2 is a very difficult real-time strategy game where people dedicate their lives to get as good at this game as possible. There are professional tournaments in this game, and it has the largest prize pool of any esports. And I believe last year the total global prize pool was $40 million. I want to show you a quick video of the bot playing the game at TI, which is the tournament, the international, where we played in August, where we played close games with some of the best pro teams, but we didn't win. But I want to show you a clip. Now, the game is very complicated and it's hard to understand. So here's what you need to pay attention to. At some point, you'll hear the casters being impressed. So now, behold. Wait.
No, that's going to be fine, but yet another death that OpenAI takes.
Wait, these are your professional players. They do this for a living. That's just, wow, I'm so sorry.
So the green one,
Well, and yeah, here comes the...
this one is,
didn't do the maths. Yeah, didn't do the maths. OpenAI is beyond math. You don't understand.
anyway, you got all the information you needed. Speaking of OpenAI 5, we will have our finals on April 13, where we will showcase new capabilities that we've never showcased before, and we will play against the current strongest team in the world, OG. So that's going to be a fun event. Now, one of the lessons, the useful lessons we learned from building OpenAI 5 is that the story of deep learning applies to RL. But wait, what's the story of deep learning? The story of deep learning is this. Empirically, old simple methods, which were usually invented in the 80s and the 90s, when scaled up on very large clusters, work really well. That happened with computer vision, that happened with normal supervised learning, and it's also happened with RL. We basically took a normal, simple reinforcement learning method, scaled it up, and discovered that it suddenly becomes very capable of solving extremely hard problems. So that's new information. It gives us another very powerful tool in our arsenal. But one way you could criticize our work is by pointing out that we had to use very many thousands of years of gameplay. In contrast, a top human needs only 5 years of gameplay. So that's a very substantial difference. And from this, some concluded that reinforcement learning cannot be used for anything in the real world. A sensible conclusion if everything truly requires thousands of years of continuous experience. In response to this criticism, we've developed Dactyl, which was a reinforcement learning system trained in simulation. But we used a very simple idea, which is called domain randomization, which basically allowed the learned policy to adapt on the fly to the real physical robot to solve this kind of task. So even though we had a very large amount of experience in simulation, the amount of experience used on the real robot was much smaller. So that's good. That's encouraging. While this work is a partial rebuttal to the criticism that reinforcement learning requires unfeasible amounts of experience in order to be useful, it is not a complete rebuttal. We still need a very large amount of experience in simulation. And perhaps importantly, we are not making use of an important source of information, which is the real world itself, just the data that continuously comes our way. I want to just show one other video. It is another research project we've done last year, which I'm very fond of, where we've shown how by simply asking your reinforcement learning agent to not be bored, you can learn very interesting behaviors. And I want to show you one of them. So here you see the agent playing Mario, and it was asked not to be bored. It hasn't been asked to maximize the score. And if you pay attention, you'll notice that it doesn't doesn't try to pursue coins. It just does things which interests it, which are novel. So see, there are all these coins it doesn't take. See, it skips all of them because it doesn't know that they're interesting. All it knows is that if it loses a level, it will be bored because it will go to a place where it's seen before. And so, it keeps on playing, and it's pretty decent, and it was able to pass very many levels, and it was able to pass the boss. So that is a very encouraging, fun result, which I like. Now, with all this context and background, with all this background context and reinforcement learning, we can now start talking about unsupervised learning. Now, why should we talk about unsupervised learning? The answer is, in the end of the day, we want to build systems that make use of all available information. Reinforcement learning systems, as they're designed today, they primarily make use of the reward signal only. But they don't make direct use of the information that exists in the world. They don't try to model the world. The thing that I want to tell you about reinforcement learning here, unsupervised learning, I misspoke. The main takeaway that you should take from unsupervised learning is that the deep learning story, which happened with supervised learning, where once you got big neural networks, big convolutional neural networks that suddenly began to work, and in reinforcement learning, where if you take an old and simple reinforcement learning algorithm and you scale it up, you can suddenly solve extremely hard problems which were believed to be completely unsolvable in the past, like we've shown with OpenAI 5. I want to convince you that the same thing is happening with unsupervised learning right now. The same story. Unsupervised learning was correct all along. Our models were too small. In fact, here's a slide which shows exactly what I've told you, but in pictures. Before, we had slow computers, and our model class was good, but perhaps not quite as good as we have right now, the LSTM, and unsupervised learning doesn't work. Today, with a much larger amount of compute spent on deep learning, plus improved architectures, unsupervised learning seems to work. And I want to give you the evidence and the explanation so that by the end of my presentation, you will not only be convinced of the evidence, you will also understand for yourself why it is so. So, warning. The next few slides are going to be technical. There's only 3 or 4 of them. If you're not interested, you should feel free to zone out, and I'll tell you when you can pay attention again. But the goal of the next few slides is to explain to you the unsupervised learning cost function and to explain to you attention. So, let's begin. As we know, in deep learning and in machine learning in general, the most important thing is the cost function. You need to know what you're optimizing. Once you know what you're optimizing, you can optimize it with our extremely powerful tools, with the large clusters, and then you'll get a good result. So here's what I want to convince you, that if you have a model which is really big and powerful, and you ask of it to predict the next word sufficiently well, and it succeeds, then it means that it understands the text. So here's the statement I'm going to make here. Predicting the next word in text sufficiently well will lead to understanding of the text. And as a byproduct, if you can predict the next word sufficiently well, you can also generate text because you just make a prediction and you feed it back to yourself. But let's analyze this argument. Why should it be that predicting the next word sufficiently well will lead to understanding of the text? Actual understanding, true understanding. Well, let's work out some examples. Let's say you are reading a legal document, and it has a lot of text in it, there's lots of stuff, but you can predict the next word. Like, ultimately, the only way to do it well enough is because you understand what it's talking about. Let's say you're reading a murder mystery, and at some point, the text reveals the identity of the criminal. Well, there's going to be a word in the text which says, and like, person so-and-so. Well, if your model can predict so-and-so, it means that the model must have figured out the meaning of the text. That's basically the idea. That's the crux of it. let's think of on one more example. Let's say you're reading a math textbook, and you open in the first page, and it's kind of confusing at first. But as you understand the text better, it becomes easier to read the text, because you see, oh, like they say, let's use this lemma in such and such way, and it's pretty easy to understand. It's very predictable, versus the whole thing looks like a random, incomprehensible mess. So the argument is that if you ask your machine learning model, if you ask your deep neural network to predict the next word well enough, unsupervised learning will happen, understanding will happen. This is a claim. Let's look at it. But the claim will turn out to be true. But this is the idea. To sum it up, predicting the next word well enough equals understanding. That's step one. Step two, I want to tell you about one of the most important innovations in neural network architectures in recent history. There's basically been a small number of them. There's been the LSTM, the convolutional neural network, and attention. And I want to explain attention to you. Attention is very important. Many of you should be familiar with the concept of a dictionary, which can store key value pairs. So attention is nothing but a neural dictionary, where you have a set of key value pairs and a query, and the query basically is matched against all the keys, and you output the value. And the whole thing is done in a way that's differentiable, so you can train it with backpropagation. Now you may say, OK, that's a totally ad hoc thing. Why would you care about it at all? And the answer is, in short, is that when you predict the next text, when you want to predict text, the ability to do these neural dictionary lookups is helpful for referencing things in the past of the text. So you just have this like dictionaries on top of dictionaries which reference things back in complicated ways. So you can deal with very long context histories. So that's it. This is the concept of soft attention, the most important idea in neural network architectures, basically since the LSTM. OK, this is the last technical slide. Unsupervised learning is achieved through sufficiently good prediction of the next word, which is done with a modern architecture which uses a lot of attention. But also, the way you make those models good is by making them large. Use large clusters, use lots of GPUs, and you train them on lots of data. By doing that, the model becomes good. The magic of deep learning kicks in, where models train on more data with more parameters just get better. And the second idea is that attention is a neural dictionary, and that's the most important architectural idea since the LSTM. Great. So at this point, the technical slides are over, and we will go to an overview of the results. Now, the GPT-2 was not a project that was created spontaneously. It is the culmination of several years of work. Our first result in this direction was the sentiment neuron, which some of you may have heard about. It was a very similar idea in spirit. The intuition was that if you train a neural network to predict the next word, or sorry, the next character in a large number of Amazon reviews, then one of the neurons of that neural network will learn to represent the sentiment of the review. And that makes sense because reviews are usually positive or negative, and to predict the next character well enough, at some point you need to know the sentiment. That turned out to be true. And that X model was run on 4 GPUs, 4 Pascal GPUs for a month, which was at the time a lot. Then, a year later, we've released the GPT, which at this point was a transformer. And by the way, a transformer is a neural network architecture which is a very good way of putting attention together. It's an attention-based neural network architecture. It trains really well. It's fantastic. And we've trained the GPT on the books corpus, which was a different data set. And we trained it on 8 Pascal GPUs for a month. And as a result of doing this, we were able to achieve a large improvement on a fairly large number of natural language processing tasks. The reason it happened, by the way, is because natural language processing has this feature that you've got this very large number of tasks that measure different kinds of language understanding, and each task doesn't have a lot of supervised data. And what it means is that, well, if you don't have a lot of supervised data, it means that unsupervised learning will be especially helpful, which is what we've seen. At this point, it is important that I mention highly relevant historical work, which puts our GPT work in context. There are several other related works. In 2015, Kwok Lee and Andrew Dai, they've trained a model, an LSTM model, to predict the next word, and they've shown some very promising transfer results. They've also been Elmo from the Allen Institute, which showed even better such results, and UML Fit from Fast.ai, which showed even better results. Then we've got our GPT, which showed even better results on the different NLP tasks. After this, BERT from Google was released. But then we released the GPT-2, which was far better than everything that came before it. And our primary innovation has been to use a larger model on a larger data set. So this is, again, a repetition of the story of deep learning. Just like with supervised learning, where convolutional neural networks with backpropagation were basically the correct idea all along. Just that when your convolutional neural network is so small, what can it do? If you only have 20 neurons, you're not going to do much. But if you have 100,000 neurons, you can do something. And like I mentioned earlier, the same thing happened with reinforcement learning, where if you take your reinforcement learning method and you make it run at larger scale, then suddenly it can do things it couldn't do before. Suddenly it can solve problems that were believed to be fundamentally unsolvable. And I'm referring to Dota. Like, right now, we take it for granted that you can just solve real-time strategy games with reinforcement learning. But I don't know how many of you were those of you who were into reinforcement learning, just try to rewind 2 years back and try to imagine just applying a simple reinforcement learning algorithm and solving a real-time strategy game. At that time, you could barely solve Atari games. So it is really a repeat of the deep learning story. You take a simple tool which is unimposing and barely works, and then you run it on a big cluster, and suddenly it works. It becomes a capable tool for solving problems. And we're seeing the same with unsupervised learning and text generation. Just train a bigger model and more data. The transformer has 1.5 billion parameters, which is, of course, still a small model. But we used a data set, which we call WebText, which has lots of variety. And this model was trained on 100 voltas for a week. So a bit more compute, but still perhaps nothing too outrageous yet. Now I want to review some of the results of the GPT-2. I'm going to show you some plots. The important thing you need to know from the plots is an analysis where bigger models work better on different downstream tasks. So we take our GPT-2 and we apply it to various tasks directly. Without any additional training, we just plug it in. We plug it into various tasks, and we see how performance gets better almost always as you make the model larger. With the exception of, I believe this is summarization, is what I'm showing you. But I'll show you summarization, how summarization works. It's really neat. So one really neat thing about the GPT-2 is that it works so well that you can apply it to various NLP tasks with no additional training whatsoever. For example, there are all these tasks which are shown on this slide. You don't need to know what they are. I mean, you do. It's kind of cool, but I won't explain them what they are. The thing that you need to know is that all these tasks, we've achieved a significant improvement in state of the art over previous state of the art, like a very significant improvement. But we also didn't use any of the training data for these tasks. We simply used the language model as it was trained on our big corpus, and it just worked. And I want to show you a little bit of what it means, how exactly we apply the language model towards a new task. For example, let's look at the Vinograd Schema Challenge. The Vinograd Schema Challenge is a data set where we've achieved a very large improvement of a state of the art from a certain score of 63 to a score of 70. So from 63 to 70, it's a very big jump, where human performance is 90. And I want to give you just an illustration of what the task means. So you got this sentence The trophy doesn't fit into the brown suitcase because it is too large. So what does it refer to? Does it refer to the trophy or does it refer to the suitcase? The trophy doesn't fit into the brown suitcase because it is too large. Well, it must be the trophy because the trophy is too large and therefore it doesn't fit into the suitcase. But here's a different version of the sentence. The trophy doesn't fit into the brown suitcase because it is too small. Well, now it refers to the suitcase because it doesn't make sense otherwise. So these are example sentences where you need common sense. You need to have world knowledge. You need to understand that suitcases have sizes, and trophies have sizes, and large objects don't fit into small objects. You need to know all those things. And the way you can just use the model is as follows. What you do is that you just take the word it, and you replace it with suitcase, and you show it to the language model, and you ask it for its probability of the sentence. So you plug in the two words, and you compare the probabilities of the sentence, and you select the better word. And in this case, the model did the right thing. And in fact, it did so in 70% of the cases. So we are making progress, and this gives us some evidence, it gives us some confidence that the model that just been trained on text is actually learning some things about the real world. Let's see. Here's another cool thing, question answering. It's far from matching state of the art yet, but it is still interesting that you can just take the model and ask it a question, put a question mark, and just the model will generate an answer. So let's see, for example, you ask it things like, who wrote the book, The Origin of Species? And it says Charles Darwin. So these are, on this slide, I'm showing you the answers, the questions for which the model has confident answers. And this is unrestricted. We don't give it multiple choices. We just say, produce the characters, or in our case, the byte pair encoding, but you should think of it as for this characters. Produce the characters of the answer. And it makes some cool, fun mistakes, like, who played John Connor in the original Terminator? And it says Arnold Schwarzenegger. Nuclear power plant that blew up in Russia, ? Chernobyl. It got that one right. So it has all kinds of world knowledge. And what we are seeing is that as the model becomes larger, it eventually starts to use a greater fraction of its capacity to learn all kinds of random facts. So that's cool and encouraging. Here's a summarization example, which is quite cool, where you don't need to read all this. Here's the important thing. You give it those two, you have a data set, we got these kind of paragraphs of text. You take those two paragraphs, and then you have questions about it. So the data set will have like 8 or 9 questions about this paragraph. So then the way you would use the model to answer questions about this paragraph is that you take these two paragraphs, you'd concatenate them. You would then prime the model by giving it all these question answer pairs as a follow-up to the paragraph. Then you write the question, and then the model will just spit out an answer, again, essentially character by character, essentially unrestricted. And the cool thing is that in this particular example, the humans say, the question was, there's some text, it doesn't matter what it is. The question say, and did they climb any mountains? The humans say unknown or yes. The model says Everest. Everest is the correct answer. So it is quite nice. Now I want to show you how you summarize. I'll just be really brief. To summarize a paragraph, you just append TLDR. And of course, all these results are without fine-tuning, and you can get better results with fine-tuning. I want to show you, well, I want to just read to you a fraction of our favorite sample from GPT of all time. I will read only a fraction of it, but it is pretty neat. Now, I also preface by saying that we needed to run the model many times before we found a sample this cool. And we did all kinds of tricks like truncation and lower temperature to increase the quality of the samples. But with these caveats, it's still quite cool in my opinion. So we told the model, recycling is good for the world. And then we followed up, no, you could not be more wrong, with exclamation marks, fully capitalized. And then let's see what the model says. It says, recycling is not good for the world. It is bad for the environment. It is bad for our health, and it is bad for our economy. I am not kidding. Recycling is not good for the environment. It is destructive to the earth, and it is a major contributor to global warming. recycling is not good for our health. It contributes to obesity and diseases like heart disease and cancer. I didn't know that. Recycling is bad for our economy. It increases the cost of a product and in turn the price of everything that is made with that product. So I read only the first third. It goes on like this. Eventually, it starts, you can notice that some things don't make fully sense, but that was pretty good. And I want to show you another cool thing, which is, so we didn't release the large GPT model, but we released a small GPT model, which is 1/10 of the size of the large GPT model. And some people on the machine learning subreddit have tried it out. And I want to show you one particular example, which is, so the first comment is the context, and then the second comment is the completion by the model. And this was done by some third-party people on Reddit. So the first person says, US stocks closed flat on Tuesday as a solid rally faded on concerns about US-China trade talks. Markets came under pressure after Bloomberg News reported that some US officials fear China is walking back to trade pledges. Investors will turn their attention on Wednesday to the conclusion of the Federal Reserve's two-day meeting and press conference from the Fed chief, Jerome Powell. So this was the context, and now here is the model continuing its output. The Fed is expected to decide on March 1st whether to extend the central bank's policy limit until next June. In light of the recent Fed actions in recent months, the US Federal Reserve should look at more ways it can mitigate long-term volatility. The US could also consider moving into additional buyback mechanisms if it sees it is unable to meet its fiscal targets, like those agreed to by the Japanese government. In view of the uncertainty and uncertainty surrounding the future of the Fed policy, it is important that we try to maintain long-term bond yields over a long period of time to ensure sustainable growth scenarios, says Robert Vickers, Chief Market Strategist at Credit Suisse. So the model wrote all that, the small model. And then someone replied by saying, I can see how GPT-2 could maliciously be used to generate believable fake news. And I want to talk about that. I want to finish with the partial release and our thinking behind it. Fundamentally, our thinking is as follows. Machine learning is becoming more powerful and more impactful. This leads to amazing applications, but it also leads to a potential for malicious use. And today, there exists no norms or mechanisms for publishing or disclosing work with this nature. And with publishing, you can always publish, but you can't unpublish. So we decided to not publish the large GPT model. And if this, the way I think about it, this is just a taste of what will happen. If you believe, if you think it's likely or even plausible that deep learning will continue to produce amazing advances as it becomes larger, as it's trained on more data, and as improved training methods and architectures are developed, as they have been over the past 6 years, then we should expect that in the future, there will be a lot more applications of this kind, where the people who will develop them will start to feel quite uncomfortable about just releasing them like they've always done in the past. And it's kind of frustrating, but it is in some way the ultimate, you know how you have problems of failure and problems of success? So for example, if a scientific field is not flourishing, then the number of people at the conferences will start to decline year after year. But if the field is flourishing, then the number of people at the conference will increase very rapidly, and suddenly people will start complaining with things like, well, that's not fun. The conference used to be nice and cool, and I got to see all the people that I know, and now you can't run into anyone. It's too big. It's so commercial. Those are problems of success, and so is this. Our tools are powerful. They're impactful. They will be more impactful in the future. We'll need to face this issue of what to do when our tools are that powerful. And that's all I have to say. So thank you very much for your attention, and I'll be happy to answer a few questions.
Thank you, Ilya. The microphones are in the aisles. Please.
Does GPT-2 pass the Turing test?
No.
Great. Thanks for your presentation. I have a quick question. You mentioned that, especially the question answering applications, do you have any efforts in trying to understand why the model is answering the questions like it does? And do you think that, like, if we can, you mentioned if we can model like predicting the next world, then the model must have modeled and understood all the text. So can we query the model to know how it's making decisions?
So that's a really good question. Right now, the model is not very easily interpretable, and it is right now also hard to tell in advance what kind of data it will choose to focus on. There is lots of data in the text, and the model, by trying to predict the next word, by maximizing the likelihood, and I'm going to get a little technical, it basically tries to go for the more salient and more frequent patterns first, and then for the more random stuff and the longer tail later. So it will try to say, okay, I'm noticing some regularity, and I will try to predict this regularity better, and I'm going to make poor prediction on all the like obscure questions. Now, to get a more specific answer beyond that is hard, and so we are trying to understand what the model is doing. We have a battery of tasks. We measure the model's performance, and it's going to be expanded in the future, but it's not a trivial matter to understand exactly what it is that the model knows and what is hiding in its weights.
Hi there. Regarding responsible disclosure, you were really pioneering this new method of releasing your research here. How do you feel that that the industry and that science and that the media reacted to the release? Did this meet your expectations?
That's a very good question. No, it didn't meet my expectations. I didn't expect anywhere near such a polarized reaction. But I mean, the conclusion from this is that people have strong feelings about it, and it's going to take some time before the research community will figure out what to do about the fact that our technology is getting more powerful.
Yeah, thanks for the talk. One of the things you mentioned was training across a bunch of Volta V100s. And as I understand it, one of the big selling points of that card was that it had sort of the dedicated matrix multiplication units in each of the SMs. And of course, the Google approach is that you have this big systolic matrix multiplier. So my question is there anything in attention models or deep reinforcement learning going into the future that we should, besides dense matrix multiplication, that we could consider supporting in hardware?
That's a good... Yeah, that's a good question. What should the hardware support? I think the current devices are pretty good. Fast interconnects between devices can be good. And perhaps more support for sparsity, that can be another good thing to explore. Right now, we mostly use blocky dense compute. Now, sparsity is a possibility. It doesn't mean it will be important. It's something which could be important. Connecting these devices is very important.
What do you think of attention?
That's all you need.
So maybe we should put that into hardware.
I mean, it's just it's a very natural fit for the existing block matrix multipliers.
So your language model is left context the next words.
Yeah.
The vinegar challenge, if you look at that context, actually, whether it's suitcase or trophy is on the right, whether it's large and small. So how do you explain that prediction? When you look at the left, their sentences are exactly the same. You had the...
Yeah, so this is a technical question, and I'll give you a brief technical answer. The model predicts the next word, but then you look at your sentence, and you add up all your prediction errors across the sentence from beginning to end. And that's how you get a score for a sentence as to how likely it is. And you compare those scores. So the scores look at the whole sentence in its totality.
Is OpenAI looking into aspect-based or entity-based sentiment in any way? And if so, can you share with us any developments?
Sorry, can you repeat the question? I didn't hear.
Are you
What's-
looking into aspect-based sentiment or entity-based sentiment at all?
I probably not, because I don't know what it means.
Okay, thank you.
So I had a question regarding the question answering task. Like you talked about word prediction, but how do you go from word prediction to the answer? Like it's not very clear to me. And the second question was regarding, say, conversational agents, where generally when we are conversing between humans, you tend to ask follow-up questions to refine your state of current knowledge. So like many times I don't understand this, I'll ask a follow-up question so that I update my knowledge. So how do you think this model can be updated? Like can it ask probing questions to expand the knowledge? Yeah.
I think the easiest path there is to collect a special data set with lots of collect a large data set with lots of questions, with lots of conversational data, and that will train the model to do the kind of thing you were describing. Now, how good it's going to be, it's currently unknown.
Another question on the Turing test. So you mentioned this does not pass it. So do you think this would still be the future direction to pass it? Is more model on a bigger model on more data on maybe more different types of data sets?
Well, I don't know if it will literally pass the Turing test, but it seems hard to see how, training bigger models is going to be better. It's going to work better.
Thank you.
Okay, time for the last question.
So I have a question. I guess it's sort of related to the Turing test question, but one of the things that it strikes me is some of this comes to a question of like, how do you validate the quality of the prediction, which in some cases could be, does it emulate the style of the content that the model is based on? But in other cases, like the recycling example, there's sort of facts that it gets wrong. So are you guys also looking at other ways to sort of when the output is fact-based as opposed to just sort of being a type of content, are you guys looking at other ways to kind of refine the model?
Evaluating the model, or for evaluating any machine learning system in general, is a pretty not easy thing to do. And all the issues, if you think about, for example, evaluating a vision system, it's not that easy. You can have a test set, and you can develop a test set, but what if the data you care about is in some way different from the test set? So then you may do poorly on the data you care about, but do well in your test set. And it's just a hard problem, which is currently unsolved. And we face the same problems where, yes, we have the model. Yes, we have a battery of tests. We can run the model against the tests and make various conclusions from its performance on those tests, and try then to make educated guesses about its properties and about, for example, its commands of facts, etc. So that's my answer. And that's all I have. So thank you very much for your attention.